This world is not what you think it is. This world is not what you think it is.
We still have flat earthers. We have people that don't believe in vaccinations. And what do we do about it? Well, first of all, I think there's a gene. I think there's a gene for superstition, a gene for hearsay, a gene for magic, a gene for magical thinking. And I think that when we were in the forest, that gene actually helped us. Because 9 times out of 10, that gene was wrong. Superstition didn't work. But 1 time out of 10, it saved your butt. That's why the gene is still here. The gene for superstition and magic. Now, there's no gene for science. Science is based on things that are reproducible, testable. It's a long process, the scientific method. It's not part of our natural thinking. It's an acquired taste. It's like broccoli. You have to learn how the power can be unleashed by looking at your diet, for example. So I think 1,000 years from now, we will have flat earthers.
There is a crisis in cosmology. Usually in science, if we're off by a factor of 2 or a factor of 10, we call that horrible. We say something's wrong with the theory. We're off by a factor of 10. However, in cosmology, we're off by a factor of 10 to the 120. That is 1 with 120 zeros. This is the largest mismatch between theory and experiment in the history of science.
How do we know the Earth is not flat?
We don't.
We are prisoners on Earth.
It's flat.
Space station taunts us by showing us all the places we can't ever visit. However, if our species wants to have a long-term future, we have to escape our prison. But what's keeping us here in the first place, alive? Turns out, we owe the universe a debt. Gravity, the line. This effect traps us. We can imagine this as stories to describe the world. We test our stories and look to reality up close.
It's flat.
And we're amazed. Wondrous landscapes in the dust. We test our stories. We test our stories. We test our stories. And we're amazed. We test our stories. We test our stories. We test our stories. And we're amazed.
A science delusion is the belief that science already understands the nature of reality in principle, leaving only the details to be filled in. This is a very widespread belief in our society. It's the kind of belief system of people who say, I don't believe in God, I believe in science. It's a belief system which has now been spread to the entire world. But there's a conflict in the heart of science between science as a method of inquiry based on reason, evidence, hypothesis, and collective investigation, and science as a belief system or a worldview. And unfortunately, the worldview aspect of science has come to inhibit and constrict the free inquiry, which is the very lifeblood of the scientific endeavor. Since the late 19th century, science has been conducted under the aspect of a belief system or worldview, which is essentially that of materialism, philosophical materialism. And the sciences are now wholly owned subsidiaries of the materialist worldview.
Several decades ago, we found a problem so great that it was brushed under the carpet for many a decade. And this is the fact that galaxies spin too fast. We believe in the work of Isaac Newton, at least on planetary scales, but when you apply Newton's laws of motion to the galaxy spins too fast. In fact, 10 times too fast. By rights, the galaxy should fly apart. Therefore, scientists said that we have to have dark matter, a halo of matter that surrounds the galaxy and holds the galaxy together.
Between 1% and 3% of the universe is all the stuff we can see, and somewhere between 99 and 97% of the universe is stuff we can't see. This dark matter that dominates our galaxy, we think, we're virtually certain now, is made of some new type of elementary particle, different than the stuff that makes you and I up.
And what have they discovered? Absolutely nothing. Zilch.
What is a little bit perturbing is that after 50 years we still haven't found what the dark matter is. But on the other hand, that doesn't mean they're not there, it just means they're harder to find than we thought.
We look out in the universe and 85% of all the gravity that's out there has some mysterious unknown source. We add up all the stars, the galaxies, the planets, the comets, the black holes, the dark clouds, everything out there that we can see, touch, smell, or taste. And it doesn't add up to give us the gravity that we see operating in this universe. So really we should be calling it the dark force, because we don't know if it's made of matter. It could be a profound misnomer, sending people off in thought directions that might not really be the right path. So dark matter is just simply what we call this thing about which we know nothing, responsible for 85% of the gravity of the cosmos. We've known about dark matter since the 1930s. Back then it was called missing mass. That's what it was called. Because, yeah, there's got to be some mass. Where is it? We can't find it. It's got to be here somewhere, because we got the gravity. If you have the gravity, you got to have the mass. Mass and gravity go together. It's really dark gravity. Actually, we shouldn't call it anything. We should call it Fred. Something that has no meaning, because we don't know what it is to call it. But it is the longest standing unsolved problem in modern astrophysics. Dark matter, dark energy. Everything we know about the universe, what we're made of, galaxies, stars, planets, that's all right here. So, according to this chart, we are 96% stupid.
So the problem with cosmology is that we keep inventing theories, ad hoc theories, to try to explain the data, such as inflation, dark matter, dark energy, and so on, just to keep patching the theory up.
There is a crisis in cosmology. Usually in science, if we're off by a factor of 2 or a factor of 10, we call that horrible. We say something's wrong with the theory. We're off by a factor of 10. However, in cosmology, we're off by a factor of 10 to the 120. That is 1 with 120 zeros after. This is the largest mismatch between theory and experiment in the history of science.
This is the universe, home of the Whopper. I'm your host, Stephen DeGrasse Colbert. Yes. DeGrasse. Turns out you can't copyright a middle name. Here aboard my ship of the imagination, the Green Screen 5000. We are freed from the constraints of space and time using these controls: a warp field neuralizer and a hot glued speak and spell. We can travel anywhere our imagination leads us, as long as my graphics team can crank it out in an afternoon.
I'm Neil deGrasse Tyson, bitch.
So from nothingness comes somethingness.
Yes.
Okay.
And by the way, just to put you at ease with that,
please,
because the way you said that was all pejorative. Just want you to know.
It was. It had a little majority to it.
You copped a little attitude on
I did.
that.
I was like, and I wasn't really excited with the answer. I was like, it didn't really answer anything for me.
How do you get something from nothing? So let's say you have. Oh, let me save the answer to that for after the break.
The answer to this, Mr. Bender, next week.
When we come back on Star Talk, we'll find out how you get something from nothing on this edition of Cosmic Queries, Everyday Astrophysics.
I'm Neil deGrasse Tyson, bitch.
So you've got questions?
I've got questions.
And it's on Everyday Astrophysics.
Yeah.
Bring it on.
Actually, you left me hanging on the last. There was a big cliffhanger that we left on, and you didn't finish it for me.
I forgot,
and I almost forgot too.
Okay,
because you greased me out of it.
Oh yeah, I did. I said nice things about you. Hey, it's all about me.
Yeah. I was like, I'm listening.
So the question was, how do you get something out of nothing?
Mm-hmm.
So the thing is, with energy, you can have positive energy and negative energy. It's not just an emotional thing; it's actually a real physical thing in the physical universe, and each of those have consequences on space, time, and matter. But if you bring them together, it sums to no energy at all. So how does this happen? So think about it. Let's say there's level ground, and then I have a shovel, and I put ground from this part, and I stack it over here. So I'm digging a hole,
right,
and making a mound. Well, I can keep doing this, and I can have a hill as arbitrarily as high as I want, and I can climb to the top of the Empire State Building. But there's a hole next to it. So how did I get that high? How is that even possible? I took the dirt over here and I put it over here. But if I put the dirt back in, then everything's level again. So it's a way to think about what it means when you have negative energy and positive energy. There are a lot of things we do where you started with nothing, but you ended with something that you care about. But in the total picture, it sums to zero.
I see. That's good. Now that's a good explanation.
That's what I'm saying.
That I can walk away with and go, okay, I get that,
and not lose sleep tonight. Good.
Yeah, I would have lost sleep. I would have been.
Neil deGrasse Tyson's explanation of the Big Bang and how you get something from nothing. Watch this man do his fake yawn. He knows Neil is just spouting out a load of crap.
And then I have a shovel, and I put ground from this part, and I stack it over here. So I'm digging a hole,
right,
and making a mound. Well, I can keep doing this, and I can have a hill as arbitrarily as high as I want.
I'm sorry, I'm allergic to bullshit.
But physicists who make up the laws of nature are less constrained by them than most of us. And in the 1980s, people who were studying galaxies found that the galaxies weren't behaving as they ought to. These stars in the galaxies were revolving around the center far too fast, according to the amount of matter there should be in the galaxy. And galaxies were attracting each other too strongly to be explained in terms of the total amount of matter within them. If you add up all the matter within them, stars, planets, gas clouds, make generous assumptions for invisible stars and so on, there's not enough matter to explain the gravitational pull of one galaxy on another, or of a galaxy on its outlying stars. So there was a terrible dilemma. What to do? Either the theories on which cosmology were based, Newtonian or Einsteinian relativity and gravitation, were wrong, or there was some organizing principle in galaxies over and above gravity that scientists had missed out. Or there must be a lot more mass that we couldn't see within the galaxies that could explain the missing gravitational effect. Well, the least disruptive assumption for scientists was that there was a lot more matter that we couldn't see, and because we can't see it, it was called dark matter. So they postulated that there was dark matter in the galaxies that would explain these phenomena. The distribution of dark matter could be adjusted for each galaxy to explain its shape and its behavior. How much dark matter did each one have? Well, the answer is simple. You just titrate in as much dark matter as you need to make the equations balance and explain the form of the galaxy. And that's the prevailing view. There are still minorities in science who think that there have to be other ways of thinking of galaxies or modifying gravitational theory, but the great majority take the view that dark matter's real. However, the problem with that is that there's not a shred of evidence for its existence. Despite billions of dollars being spent on dark matter detectors, underground pits full of fluids and so on, not a shred of evidence has emerged that it actually exists. The only evidence for it is that it makes the equations balance and enables the conventional theories of physics to survive any test, because you can add in more dark matter or subtract it as required to explain what you want to explain. It's basically an untestable theory. They've tried to test it, the tests have failed, but nobody's given up the theory because it fits the theories that they want to believe in. Now, this led to a serious problem because having magnified the amount of energy in the universe by about 5-fold through dark matter, far more of it than regular matter, that meant the whole universe had far more gravitation than people had previously thought. And that would mean that the expansion of the universe following the Big Bang, the expansion that's still going on, should be slowing down owing to all this extra matter within the universe. And in the 1990s, people thought that the universe would stop expanding, it would finally reach an ultimate limit, and then be pulled back together by all this matter in the universe gravitationally, until the whole thing ended in the opposite of the Big Bang, known in the trade as the Big Crunch. And the whole thing would end in tears. Well, that was the general view in the 1990s. But about 1999, observations of distant galaxies revealed that far from slowing down in their recession from us, they were speeding up. The universe was expanding faster and faster all the time, the exact opposite of the prediction of the dark matter theory. So, what to do? Well, again, you can't modify the fundamental assumptions because they're fixed. So, they did modify it in the sense that they said, well, there must be an extra form of energy pushing the universe apart. And we'll call that dark energy. And it's dark energy because it's undetectable by anything other than its effects, namely pushing the universe apart faster and faster. The problem is, this has now led to a tremendous problem for the principle of conservation of matter and energy, because the main theory of dark energy is that the density of dark energy is uniform throughout the universe and remains uniform. But since the universe is getting bigger, that means there must be more of it. So the universe is now a perpetual motion machine. It's actually creating energy as it expands. So, is the law of conservation of matter and energy valid? Physicists have made up matter and energy in the last 20 or 30 years till they made up matter and energy. Dark matter and energy is now 95% of reality. Can it be converted into regular matter? Could some matter suddenly appear in this room as a result of being transformed from dark matter or dark energy? Well, nobody knows, because no one knows anything about dark matter and dark energy. So we're left with this it's as if physics has discovered the cosmic unconscious. 95% of reality is utterly unknown to us, and yet it's pervading this room.
Through your career and your writing and your acting, you've inspired so many people to enter the sciences. How do you balance science with science fiction?
They're both the same.
Now, dark matter is not even what we should be calling it, because that implies that it's matter. It implies we know something about it that we actually don't. So a more precise labeling for it would be dark gravity. Now, if I called it dark gravity, are you going to say, does dark gravity really exist? I'd say, yeah, because 85% of the gravity has no known origin. There it is.
What is gravity?
You have no idea. Okay, next question. Wow. No, here's the difference.
Wow. No. I know. That's exactly what I wished for. Well, I actually wished for it 30,000 years ago.
It's true. Even at the speed of light, mean-spirited thoughts from the stars can take thousands or even millions of years to reach the Earth.
Bitch, matter tells space how to curve. Space tells... Yeah, matter tells space how to curve. Space tells matter how to move. It's beautiful.
That is beautiful. It sounds like the opening to a dance lesson. How do we begin?
Would be dark gravity.
I gotta say, you're totally blowing my mind right now.
That's what I do. I'm Neil deGrasse bitch. There it is. I'm Neil deGrasse Tyson. Bitch.
Totally blowing my mind right now.
I'm Neil deGrasse Tyson.
You don't see the curvature of the earth. If you are 2 millimeters above this beach ball, he just don't. That stuff is flat.
I'm Neil deGrasse Tyson, bitch. There it is. It's beautiful. I'm Neil deGrasse Tyson, bitch. I'm Neil deGrasse Tyson, bitch. I'm Neil deGrasse Tyson, bitch. Neil deGrasse Tyson, bitch.
I gotta say, you're totally blowing my mind right now.
That's what I do. I'm Neil deGrasse Tyson. A more precise
onto the surface of the moon in a precise way. There is no capability to do that today.
There is no reference to what we think it is, because in fact, we have no idea. We live in a free country. In a free society, you ought to be able to think and say whatever you want. You can and should think whatever you want. If he wants to think Earth is flat, go right ahead. You want to think the world is flat? Go right ahead.
If some of these folks were around when Columbus set sail, these guys were around when Columbus set sail. They must have been founding members of the Flat Earth Society. They'd be charter members of the Flat Earth Society.
You must consider every available option and platform to meet our goals, including industry, government, and the entire American space enterprise.
Bitch.
History is written by those who dare to dream big and do the impossible.
We gotta dare to dream big, try to do the impossible.
Bitch.
History is written by those who dare to dream big and do the impossible.
Bitch.
We keep going. Whether it's the moon, an asteroid, Mars.
The moon, Mars, asteroids, there's a lot of destinations that we could go to.
Bitch.
The moon, an asteroid, Mars, sending unmanned robotic missions out to the moons of Saturn and Jupiter.
Bitch. Now, if I called it dark gravity, are you going to say, does dark gravity really exist? I'd say, yeah. There is no reference to what we think it is, because in fact, we have no idea.
As my friend Terence McKenna used to say, modern science is based on the principle, give us one free miracle and we'll explain the rest. And the one free miracle is the appearance of all the matter and energy in the universe and all the laws that govern it from nothing in a single instant.
Is that called scientism, when you believe so much in the science you've been taught that you refuse to believe something else and it becomes your religion in a way?
Yes, scientism is where people turn science into a kind of religion. It becomes a kind of dogmatic belief system. The irony is that a lot of people think that religion's dogmatic and science is free thinking, but actually, in my experience, some of the most dogmatic people I know are people who've made science into a kind of religion.
The idea was to hang by a very, very fine quartz fiber a rod with two balls, and then put two large lead balls in the positions indicated here next to it on the side. Then, because of the attraction of the balls, there would be a slight twist of the fiber. It had to be done so delicately because the gravitational force between ordinary things is very, very tiny indeed. And there it was. And it was possible then to measure the force between these two balls. Cavendish called his experiment weighing the Earth. We're pedantic and careful today. We wouldn't let our students say that. We would have to say they're measuring the mass of the Earth. You know? But the reason he said that is the following. By a direct experiment, he was able to measure the force and the two masses and the distance, and thus determine the gravitational constant. You say, yes, but we have the same situation on the Earth. We know what the pull is, and we know what the mass of the object pulled is, and we know how far away we are, but we don't know either the mass of the Earth or the constant, but only the combination. So by measuring the constant and knowing the facts about the pull of the Earth, the mass of the Earth could be determined. So indirectly, this experiment was the first determination of how heavy or how massive is the ball on which we stand. It's a kind of an amazing achievement to find that out, and I think that's why Cavendish named his experiment that way instead of determining the constant in the gravitational equation, weighing the Earth. He incidentally was weighing the sun and everything else at the same time, because the pull of the sun is known in the same manner.
Things like the gravitational constant, the speed of light, are called the fundamental constants. Are they really constant? Well, when I got interested in this question, I tried to find out. They're given in physics handbooks. Handbooks of physics list the existing fundamental constants, tell you their value. But I wanted to see if they'd changed, so I got the old volumes of physical handbooks. I went to the Patent Office Library here in London, and they're the only place I could find that kept the old volumes. Normally people throw them away when the new values come out. They throw away the old ones. When I did this, I found that the speed of light dropped between 1928 and 1945 by about 20 kilometers per second. It's a huge drop because they're given with errors of only fractions of decimal points of error. And yet, all over the world, it dropped, and they were all getting values very similar to each other with tiny errors. And then in 1945, it went up, 48, it went up again. And then people started getting very similar values again. I was very intrigued by this, and I couldn't make sense of it. So I went to see the head of metrology at the National Physical Laboratory in Teddington. Metrology is the science in which people measure constants. And I asked him about this. I said, what do you make of this drop in the speed of light between 1928 and 1945? And he said, oh dear, he said, you've uncovered the most embarrassing episode in the history of our science. So I said, well, could the speed of light have actually dropped? And that would have amazing implications if so. He said, no, of course it couldn't have actually dropped. It's a constant. So, well then how do you explain the fact everyone was finding it going much slower during that period? Is it because they were fudging their results to get what they thought other people should be getting, and the whole thing was just produced in the minds of physicists? We don't like to use the word fudge. I said, well, what do you prefer? He said, well, we prefer to call it intellectual phase locking. So I said, well, if it was going on then, how can we be so sure it's not going on today? And that the present values are produced by intellectual phase locking. And he said, oh, we know that's not the case. I said, how do we know? He said, we've solved the problem. And I said, well, how? He said, well, we fixed the speed of light by definition in 1972. So I said, but it might still change. He said, yes, but we'd never know it because we've defined the meter in terms of the speed of light. So the units had changed with it. So he looked very pleased about that. They'd fixed that problem. But I said, well, then what about big G, the gravitational constant known in the trade as big G? It's written with a capital G, Newton's universal gravitational constant. That's varied by more than 1.3% in recent years. And it seems to vary from place to place and from time to time. And he said, oh, well, those are just errors. And unfortunately, there are quite big errors with big G. So I said, well, what if it's really changing? I mean, perhaps it is really changing. And then I looked at how they do it. What happens is they measure it in different labs. They get different values on different days, and then they average them. And then other labs around the world do the same, and they come out usually with a rather different average. And then the International Committee on Metrology meets every 10 years or so and average the ones from labs around the world to come up with the value of big G. But what if G were actually fluctuating? What if it changed? There's already evidence, actually, that it changes throughout the day and throughout the year. What if the Earth, as it moves through the galactic environment, went through patches of dark matter or other environmental factors that could alter it? Maybe they all change together. What if these errors are going up together and down together? For more than 10 years, I've been trying to persuade metrologists to look at the raw data. In fact, I'm now trying to persuade them to put it online on the internet with the dates and the actual measurements and see if they're correlated, to see if they're all up at one time, all down at another. If so, they might be fluctuating together, and that would tell us something very, very interesting. But no one has done this. They haven't done it because G's are constant. There's no point looking for changes. You see, here's a very simple example of where a dogmatic assumption actually inhibits inquiry. I myself think that the constants may vary quite considerably, well, within narrow limits, but they may all be varying. And I think the day will come when scientific journals like Nature have a weekly report on the constants, like stock market reports in newspapers. You know, this week, big G was slightly up, the charge on the electron was down, the speed of light held steady, and so on. That's one area, just one area where I think thinking less dogmatically could open things up.
One of my favourite scientists is Henry Cavendish. Even though he was part of the rich dukes of Devonshire, that family, and incredibly rich, he went to Cambridge to study natural sciences, or natural philosophy as it's called. But he had a very curious condition in that he could hardly talk to anybody. So when it came to his Viva exam after 3 years of study, he fled Cambridge rather than sit in front of the examiners because he was petrified of them. But he was one of the most brilliant scientists of that 18th century in both chemistry and physics. For chemistry, he's noted because he analysed gases in the air. He discovered there was hydrogen, which is a huge component of the universe. He called it inflammable air. So he put some acids in a container, dropped some metal like zinc into hydrochloric acid, and got the gas to come off. And then to show it was inflammable, you could set light to it, he breathed it in and blew it into a candle. Now, do not do this at home, because it blew up and took all the hairs off his face. He invented the idea of electric potential before everybody else and used to set electric currents through his body to work out the voltage was proportional to current, and he measured the current by the degree of agony he felt with the electrical current. This is not the normal sort of person. He couldn't talk to most people. He couldn't talk to women at all. His housekeeper would get a recipe for something or other, and he'd say, no, lamb tonight, leg of lamb, and leave a note for her. He wouldn't say it, he would write it. He would dine in the evening with his friends, and he would talk to them, but if he didn't know somebody, and you wanted to ask him a question, apparently you had to go to the Royal Society, and he would be in the room, and you'd address the room this question about physics, and you postulate, and if he felt in the mood, he would reply to the room. He was a very strange man, and yet he's absolutely wonderful. He invented hydrogen. People went up in hydrogen balloons and could see the world through that perspective. He did most of the experiments quietly on his own, keeping his notebooks, and it was only after his death and a persuasive campaign by Clerk Maxwell, the famous Maxwell of Maxwell's equations from Cambridge University, that he actually got the notebooks from the estate of the Dukes of Devonshire and discovered after the event that Cavendish had discovered the unit of capacitance, discovered dielectric constants, he discovered Dalton's law of partial pressures, he discovered or written about Coulomb's law, all before these guys had done it and just left it unpublished in his notebooks. Towards the end of his life, he did a crucial experiment, which is represented by these lead balls. He lived in Clapham Common, which is nowadays a very poor part of London, but there it was quite fashionable. And he built his own place. His library he built somewhere else because he didn't want anybody borrowing his books from his house. Otherwise, he would have to ask the book back and he didn't want to talk to them. So his library was 4 miles away. At the back of it, he had a big garden shed, which might seem like the size of my house. And in it, he had 2 lead balls, like this, suspended from the ceiling, only this is not to scale. This is, I mean, lead balls. Now, the real problem is that he wanted to measure the attraction between two objects due to gravity. In other words, there's a gravitational attraction between you and me, or between me and this lead ball. So he had to be a long way away to look at the experiment, otherwise he'd interfere with it. So he had an aperture, a place where he could look through, and he put a telescope out there, and he stood outside in all weathers, and he was in his 60s doing this, staring through the window to take his measurements over a year. There's another set of lead balls inside there. This experiment really is very difficult to get to work, and a technician has sawed it apart because he got so frustrated. And then right in the middle there's a bit of glass, there's a mirror which should be suspended from a torsion wire. So you'd set it up like this in his shed, and you put it like that, and this lead ball would attract that lead ball, and this lead ball would attract this one, and so it would be pushed a little bit this way and twist the wire, and that would be pushed a little bit that way, and the wire would twist, and as the wire twists, the mirror, which is dangling in there, would twist a little bit, and light which comes in would be reflected off at a slightly different angle, and all he had to do was measure the angle. He then had to move it the other way round. Oh, he didn't move this bit, he moved the lead balls round so that you had an equal and opposite effect on the other side. So instead of having, you have that configuration. He had this is a very complicated technical thing for the time. 18th century we're talking about, and he put that way round, and then it was pushed the other way, and you could then see the displacement. Moreover, you could measure the period of oscillation of this, and from that get all the properties of the wire, the torsional constant. And that enabled him to measure big G, the gravitational constant, to an accuracy of 1%. And nobody improved on that for 100 years. He didn't describe it as that. He described it as though he was weighing the Earth. He was calculating the mass of the Earth, so that when you're attracted to the Earth through gravity, it's the product of the mass of the Earth, this big gravitational constant, divided by r squared, the radius of the Earth squared, which we normally know as acceleration due to gravity. And that quantity is essentially big G, and he measured it. And nobody could do a clever experiment. So he's a father of physics, experimental physics, some of the ideas of theoretical physics, and a lot of...
Bueno.
Los naranjos.
Bueno, yo me entiendo. Jesús me mandó el cocinero por la noche a las 2 de la noche.
Pero te conviene que te entienda alguien más porque para eso cobras.
Ah, bueno, que está arriba. La sa del agua de la playa.
Abajo, los espectadores.
Espectadores, la sa que te echa a la playa.
Eso es.
No es lo de Semana Santa que los naranjos. Y Risita, coge las 20 paelleras, las amarra y las entierra en el agua. Y acuérdate, a donde las echa, que mañana tienes que ir a por ellas. Y cuando salgo, era a las 2 de la noche, había bajado la marea. Las dejé amarrar, tal como me lo dijo, las tiré, le puse un palo. Dice, llego a la cocina, eran las 2:30 de la noche. Risita, ¿qué la has hecho? Allí ya está, jefe. Ya, pues acuéstate, que mañana a las 8 te llamo para que vayas a recoger las paelleras. Y me acuesto en ya para abrir el restaurante que era el arroz. Y me llama el cocinero. Risita, ¿qué? Ve por la paellera. Venga, que las 2 de la tarde ya están aquí. Miren, bañador, en las chanclas. Todo despeinado porque no me dio tiempo nada ponerme las chanclas y el bañador. Voy a la playa, había subido la marea. Jesús. Jesús. Había subido la marea y encontré una paella. Y la encontré porque estaba la paellera agarrada, metida entre las piedras de Chipiona, del faro. Y cuando entro en el restaurante me ve el cocinero con una paellera y adentro la 20 paelleras. ¡Asómate, mira dónde llega el agua! Llegaba el agua hasta el restaurante. Había subido la marea. Sevilla. Y al último, que cuando ya salió la bien de regla, estamos llorando. Me cobró el tío la... Me cobró a 500 veces. Y ya no fui más. Me fui andando a coger los amarillos hasta hoy. Me mandó por la noche, había bajado más el agua y por la mañana había subido. Cualquiera estaba donde está la paellera, ¿sabes? A lo mejor está en el barco ese del petróleo.
En el Prestige.
En el Petrillense. Y ya no trabajé más la cocina. Ya aborrecí la cocina. Ay, ay, ay. Pues no cobré nada, me dieron el dinero del bote.
¿Había mucho dinero en el bote?
Lo que me echaban y el dinero de lo que gané, me cobraron 20 paelleras. A 500 caras, pues viste lo que me llevé yo para Sevilla. Ay, ya aborrecí la playa. Ay, hemos llorado los dos. Ya está, tú, no es para tanto, yo. A ti yo no quiero arroz, Jesús, yo no quiero arroz ni en chino, vamos.
Is that called scientism, when you believe so much in the science you've been taught that you refuse to believe something else and it becomes your religion in a way?
Yes, scientism is where people turn science into a kind of religion. It becomes a kind of dogmatic belief system. The irony is that a lot of people think that religion is dogmatic and science is free thinking. But actually, in my experience, some of the most dogmatic people I know are people who've made science into a kind of religion.
No, I mean, Earth, to the astrophysicist, oh, so you spin, when you spin pizza dough, it kind of flattens out. Yeah. Gets wider in the middle. And so Earth, throughout its life, even when it formed, it was spinning, and it got a little wider at the equator than it does at the poles. So it's not actually a sphere, it's oblate. And officially it's an oblate spheroid. That's what we call it.
500 years ago, everybody knew the Earth was flat, and 15 minutes ago, you knew that.
Not only that, it's slightly wider below the equator than above the equator.
A little chubbier.
A little chubbier.
Yeah.
Chubby's a good way. It's like pear-shaped. A little chubbier. So, it turns out the pear-shapedness is bigger than the height of Mount Everest above sea level. There's a 20,000-foot mountain in Ecuador, which is right. Ecuador is like near the equator, hence Ecuador.
Oh, you're just not giving up.
And that mountain is actually, the summit of that mountain is 1 1/3 miles higher.
"1,500 years ago, everybody knew the Earth was the center."
Wait, but you gotta know, just so you understand, we've been fed a lie our entire life.
What will it take for people to recognize that a community of scientists are learning objective truths about the natural world and that you can benefit from knowing about it?
Modern science is based on the principle of give us one free miracle and we'll explain the rest. And the one free miracle is the appearance of all the matter and energy and all the laws that govern it from nothing in a single instant. And
I could never quite get my head around that.
That's because they just plow through it.
Run the clock backwards to 13.8 billion years ago, and everything in the cosmos started out as a single point in space. In an instant, everything expanded outward from that location, forming the energy, atoms, and eventually the stars and galaxies we see today.
In the late 90s, they discovered that the universe is not slowing down in its expansion, it's speeding up, the reverse of what it should have been doing. So how do you explain that? Well, answer, there must be some other kind of energy that no one had ever known about before, called dark energy, because you can't see it or detect it in any normal way. And you add in just the right amount to explain the facts. And so they've now arrived at the position where 96% of the universe is made of dark matter and dark energy, whose nature is totally unknown to us.
Surrounding most galaxies is a huge amount of matter that is invisible. We call this matter dark matter. Perhaps even weirder, our best guess is there is 5 times as much of this dark matter as there is the ordinary matter that makes up you and me. 5 times. Do we have any evidence for dark matter beyond our astronomical observations? Well, no.
But then, how do you know the Big Bang really happened? Well, the answer is it fits their equations.
It turns out that Einstein once postulated a repulsive form of gravity in his equations. This was because he knew that ordinary matter should make the universe contract, and he needed some kind of repulsive gravity to overcome the attraction. However, when the universe was found to be expanding in the 1920s, Einstein took that extra form of gravity out of his equations. He even called it his biggest blunder.
The whole thing is a tissue of assumption and speculation. It's not a fact. It's a theory, and it's not very well supported by facts. There aren't that many facts involved. And the dark matter and dark energy are theories. There's no independent evidence for them, and nobody knows what they are.
Now, it seems that we need a repulsive kind of gravity to explain our observations. So what is the source of this new form of gravity? It turns out that if the universe has an energy field of the right kind, it can make the expansion of the universe accelerate. This form of energy is now called dark energy. Now, to be honest, we aren't sure about this dark energy hypothesis.
But these were the exact events that had to happen in order for the Milky Way galaxy to be formed, for a supernova to go off, for the Earth to rotate around the sun, and for us to exist.
Every atom in your body came from a star that exploded. You couldn't be here if stars hadn't exploded, because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution. So forget Jesus. The stars died so that you could be here.
It reminds you of who you are, a mathematical anomaly in a sea of gas, stars, and planets.
And that's the Big Bang.
Follow from cause to effect. Without the Big Bang, we do not have evolution. Without evolution, we are more likely to accept creation as an act of intelligent design by a divine creator.
If there's no God and everyone's just an accident, then all that really matters is me, me, me. Their rich, powerful corporations with their slick sun cult logos sell us idols to worship, slowly taking over the world while we tacitly believe their science, vote for their politicians, buy their products, listen to their music, watch their movies, all sacrificing our souls at the altar of materialism.
My favorite story is where we all come from. It's an amazing thing to tell you that I know where you come from, and I know where I come from. And we come from the stars, literally. You may have heard we are stardust, and you thought it was something poetic, something that was kind of a nice analogy. But your body literally had to be forged inside a star that died. And this is not something that's conjectural. This is not a theory. And I don't know why we don't do more art and literature and dance and poetry about this story that we know is true. And the amazing thing is that if you ever wanted a connection to a larger universe, you already have it. You don't need to go looking for it. It's right here inside you. So let me challenge all of you out there. I let this story change me. How's it going to change you?
I don't really have a great way to deal with everything that I've learned being an astrophysicist.
And sometimes I hide under the bed, and it's given me anxiety attacks.
It's just like the doctor said, it's nerves, and that's all. You just take your pills and you'll be fine, really.
I understand that I am a collection of atoms that came from the hearts of stars that briefly comes together and forms planets and people and everything that's in our world.
Well, it's a symptom of a type of disturbance in the chemical electrical activity of the brain, the temporal lobe. It's up here in the lateral part of the brain. It's rare, but it does cause bizarre hallucinations.
The water in my body has hydrogen from the Big Bang, from the very start of the universe. Then the oxygen came from stars that had to die. You hold your arms around yourself and you have a story that's billions of years and trillions of miles across, just in your own self.
So what's wrong with her?
We still think the temporal lobe.
Oh, what are you talking about, for Christ's sakes? Did you see her or not? She's acting like she's fucking out of her mind, psychotic.
Cling to the people that you love, and you have sex with all the wrong people, have sex with all the wrong people, have sex with all the wrong people. And you try to find some way to just kind of work out this energy that you don't know what to do with. There has to be some emotional response to that.
Well, you know what Tolstoy said. Tolstoy said, regard the society of women as a necessary unpleasantness of life and avoid it as much as possible.
What a scientist really does is tell stories. It's about the narrative. It's about the emotions. I want to sit you down and explain why what I'm doing is actually getting your money and your funding for the rest of science.
They told me that you had gone totally insane. And that your methods were unsound.
This world is not what you think it is. This world is not what you think it is.